Welcome back, Apologia 8th grade Physical Science, Week 16, Day 4. Textbook pages 275 through 279, notebook pages 226 through 228. All right, types of energy. We're going to continue discussing energy. In the last video, we focused on kinetic energy. In this video, we're going to really talk about potential energy. Okay. So we know that objects in motion have kinetic energy, but what about objects that are not in motion? Do they have energy? Well, remember at the atomic or molecular level, everything is moving, and so has some kinetic energy. But this isn't enough to cause a change. Objects that are stationary can, however, have potential energy, depending on their position or shape. All right, so potential energy is defined as energy that is stored as a result of position or shape. Potential energy is stored energy. It's ready to make something move or cause some other change. It exists even when nothing is moving. So look at example figure 8.5. Notice the apple is hanging high above the ground. Once the apple is ripe enough and its stem starts to separate from the tree branch, the apple will fall to the ground because of the force of gravity. Because of the apple's position above the earth, it has potential energy. As soon as the apple drops and begins falling to earth, the apple has kinetic energy. The stored potential energy in the hanging apple is converted to kinetic energy once the apple falls. All right, so now look at the person playing the harp. Now look at the harp in the bottom picture of 8.5. The harpist adds potential energy to the harp string by plucking it. The energy is stored in the stretched string when the harpist pulls it to one side. When she releases the string, it begins to vibrate, and so it has kinetic energy, remember, because it's now moving. The stored potential energy is converted to kinetic energy. Plucking a string and apples hanging in trees are two examples of stored potential energy. The two forms of potential energy are gravitational potential energy and elastic potential energy. Let's first start with gravitational potential energy. So the apples in the tree is an example of gravitational potential energy. Gravitational potential energy is potential energy that depends upon the object's position above the earth or the height. Look at the diver in 8.6. He also has gravitational potential energy as he stands at the end of the diving board. How did he get potential energy? How do you think? Well, he gained potential energy by climbing up the ladder to the diving board. Now, as soon as he jumps, the diver's potential energy will be converted to kinetic energy as he falls. An object's gravitational potential energy depends on the object's mass, m, its height above the earth, h, and the acceleration due to gravity, which is always 9.8 meters per second squared. You can calculate an object's gravitational potential energy, PE, in joules by using this equation. So we have here potential energy is mass times gravity times height. In other words, the gravitational potential energy of an object is equal to its weight, mg, times its height. Now, the height of an object is relative. Again, we've talked about relative things. What does that even mean? Well, the height of the apple in the tree would be measured from the ground or the surface of the earth. However, if you start out on the second story of a building and you pick up a book and carry it up to the third floor of the building, then the height you would measure to find the added potential energy would only be from the second floor to the third floor. All right. So you will always measure height from a reference point. Most often, it would be from the ground. Most often. All right. So let's look at example 8.2 and figure it out. Suppose a diver in figure 8.6 is at the top of a 10-meter high diving platform and has a mass of 80 kilograms. What is his potential energy relative to the ground? All right, step one, always write what you know, what you want to find out. It told us the mass was 80 kilograms. We know the gravity, which is 9.8 meters per second squared. It told us that he was at a 10-meter high diving platform. We want to figure out what his potential energy is. All right, what equation are we going to use? Let's write that out. Step 3, write out the equation. Let's substitute the numbers in. So we have mass times gravity times, oh my goodness, excuse me, times the height, which is 10 meters. All right, so step 4, solve the problem. Much like in the last video, when we multiply all this together, we get 7,840 kilogram meters squared per second squared. Now don't forget that a kilogram meter per second squared is actually the definition of a Newton. And then don't forget that a joule is a Newton meter. So the answer here is 7,840 joules. All right, so again, notice the units just as with the kinetic energy. These units are equal to a Newton meter, and a Newton meter is equal to a joule. So the potential energy of the diver is 7,840 joules. After he dives, this is example 8.2b. After he dives, the diver climbs out of the pool and is standing on the ground. So what is his potential energy relative to the ground? Okay, so he dove in, he got out of the pool, and he's just standing there. Well, since the diver is standing on the ground, his height above the ground would be 0. Therefore, his gravitational potential energy relative to the ground would also be 0. 0 times anything is 0. Okay. So let's talk about, we started talking first about gravitational potential energy. Now let's swing back and talk about the elastic potential energy. Think rubber band, something like that. The potential energy of the strings of the harp in figure 8.5 is called elastic potential energy. Any object that can be stretched or compressed has elastic potential energy. And in case you're not entirely sure what elastic means, it refers to an object that springs back to either their original shape after being stretched or compressed. Think about a rubber band. You can stretch out a rubber band, but when you let it go, it springs back to its original size. When you stretch the rubber band, you gave it potential energy. The farther an elastic object is stretched or compressed, the greater its potential energy. All right, so look at this guy over here shooting the bow. The boy has pulled the string back, stretching it. That gives it potential energy. Because the arrow is connected to the string, it also has potential energy. When the boy releases the bowstring, it springs back to its original position. The potential energy of the arrow is converted to kinetic energy as it flies through the air. All right, so you add an elastic potential. You also add elastic potential energy to things such as springs when you compress them. Wind-up toys have a spring connected to the winder. As you turn the winder, the spring is compressed. Then when released, the spring returns to its original shape. And as the spring unwinds, the potential energy is converted to kinetic energy, and then the toy moves. All right, bouncing balls. Bouncing balls also have elastic potential energy. When you bounce a ball against the floor, the ball squishes a bit, compressing the air inside. Then the compressed air forces the ball to spring back up into shape after hitting the ground, thrusting the ball back up. So the elastic potential energy of the compressed ball, and really the air inside, is converted to kinetic energy of the ball as it bounces back into the air. Now, let's review what we've learned and do a couple on your own. I do have a few examples I want to discuss quickly. So examples of gravitational potential energy. When you're lifting weights, you raise your weight up. That is an example of gravitational potential energy. Water behind a dam, a yo-yo before it is released, a car that is parked at the top of a hill, A book on a table right before it falls. A child at the top of a slide. River water at the top of a waterfall. And some examples of elastic potential energy: an archer's stretched bow, a bent diving board just before the diver jumps, a bouncy ball compressed at the moment it bounces off of a brick wall, a twisted rubber band which powers a little kid's toy airplane. I hope those examples helped with your understanding of these two different kinds of potential energy. All right, on your own 8.3, what factors determine the gravitational potential energy of an object? Again, the formula is potential energy equals mass times gravity times height. What type of energy does a compressed pogo stick have? Anything that is compressed or stretched has elastic potential energy. And lastly, a 55-kilogram stuntman walks up the steps from the ground to the roof of a 72.8-meter tall building. How much gravitational potential energy does he have at the top of the building? All right, step one, always write what you know. We know his mass is 55 kilograms. Gravity, as always, 9.8 meters per second squared. The height of the roof, 72.8 meters. We're trying to find the potential energy. All right, step two, write out the equation. Here you go. Step three, write out the equation substituting the numbers. Boom. Step four, solve the problem. The answer is 39,239.2.